Welcome to our lecture on the physical transformations of pure substances. Our central theme is wonderfully economical. At fixed temperature and pressure, matter tends towards the state with the lowest Gibbs energy. We shall translate that principle into the language of chemical potential and then use it to read phase diagrams. By the end, you should be able to identify stable phases, explain phase boundaries, apply the Gibbs phase rule, and compare the rather different diagrams of carbon dioxide, water, and helium. We shall finish by connecting the slopes of chemical potential curves to entropy and molar volume. As you listen, keep asking one question: which phase has the lowest chemical potential under the stated conditions? That question is the compass for the whole chapter. Let us begin by being precise about the word phase. A phase is a region of matter that is uniform in chemical composition and physical state. The number of phases is denoted by capital P. A gas is one phase even if it contains several molecular species, because the mixture is uniform. A single crystal is one phase, and two completely miscible liquids also form one liquid phase. By contrast, two immiscible liquids form two phases, even when one is broken into tiny droplets. The same distinction appears in metals. If two metals mix at the atomic scale, the alloy may be the single phase. If they separate into regions with different structures or compositions, the material is multiphase. So phase counting is not about how many substances we can name, nor how many physical pieces we can see. It is about the number of distinct, homogeneous forms of matter present. The two sketches sharpen that distinction. On the left, the color is uniform down to the microscopic scale. This is a genuine single-phase solution. On the right, blue domains are embedded within a continuous yellow matrix. The sample might look uniform from across the room, but microscopically it is a dispersion containing two phases. Think of oil droplets in water, fog droplets in air, or grains of one solid phase inside another. Interfaces separate the domains, and properties such as composition or density change abruptly as we cross an interface. A useful test is therefore this: can we travel through the sample without crossing a boundary at which the physical state or composition changes discontinuously? If yes, we remain in one phase. If not, we have entered another. This microscopic definition prevents us from confusing visual smoothness with thermodynamic uniformity. A phase transition is the spontaneous conversion of one phase into another. Familiar examples include melting, freezing, vaporization, condensation, and sublimation. At a specified pressure, a transition occurs at a characteristic temperature, which we denote T transition. At precisely that temperature, the two phases can coexist in equilibrium. Their molar Gibbs energies are equal, so converting an infinitesimal amount from one phase to the other produces no net change in Gibbs energy. Away from the transition temperature, one phase has the lower chemical potential and is thermodynamically favored. Notice that spontaneous does not necessarily mean fast. Diamond is not the stable form of carbon under ordinary conditions, yet its conversion to graphite is immensely slow because of a kinetic barrier. Thermodynamics tells us the preferred direction and equilibrium state. Kinetics tells us how rapidly that state is approached. This cooling curve provides an experimental signature of freezing. Initially, the liquid cools and its temperature falls with time. At the freezing temperature, the curve becomes nearly horizontal. Heat is still being removed, but the temperature pauses because the liquid releases latent heat as it forms the solid. That released enthalpy compensates for the heat removed by the surroundings. Once freezing is complete, no further latent heat is available and the solid resumes cooling. The plateau is characteristic of a first-order transition, where quantities such as enthalpy, entropy, and often volume change discontinuously. In a real experiment, the curve may show supercooling. The liquid briefly falls below its equilibrium freezing temperature before nucleation begins. Nevertheless, the transition plateau gives a robust way to locate the equilibrium freezing temperature even when the formation of solid is difficult to observe directly. The thermodynamic criterion for stability is expressed most cleanly through Moeller-Gibbs energy. For a pure, one-component substance, the Moeller-Gibbs energy, G sub m, is identical to the chemical potential, represented by the Greek letter mu. Chemical potential is sometimes introduced as an abstract quantity, but here it has a direct meaning. It measures the escaping or transforming tendency of a substance under the prevailing conditions. At constant temperature and pressure, the stable phase is the one with the lowest chemical potential. If solid has the lowest mu, the substance tends to be solid. If liquid has the lowest, liquid is stable, and similarly for vapor. At a phase boundary, the chemical potentials of the adjoining phases are equal. This equality is the microscopic and thermodynamic content of phase equilibrium, and it will allow us to explain every line and special point on a phase diagram. Here a sample contains more than one phase, yet the chemical potential of the substance is the same everywhere at equilibrium. It is equal within each phase and equal across their interface. Why must this be so? Imagine that the chemical potential was slightly higher in the upper region than in the lower region. Transferring matter downward would then reduce the total Gibbs energy, so the original state could not have been equilibrium. Matter would continue to move until the driving force disappeared. Equality of temperature prevents net heat flow. Equality of pressure prevents net mechanical expansion, and equality of chemical potential prevents net transfer of matter. These are parallel equilibrium conditions. The important point is that an interface does not permit a persistent chemical potential difference. At equilibrium, molecules cross in both directions, but the opposing rates and Gibbs energy changes balance. We can make the preceding argument quantitative. Transfer a small amount, dN, from location 1 to location 2. The Gibbs energy change is the chemical potential at the destination times dN minus the chemical potential at the source times dN. Therefore dG equals open bracket mu2 minus mu1 close bracket dN. If mu1 is greater than mu2, dG is negative and transfer from 1 to 2 is spontaneous. The reverse transfer would increase G. Only when mu1 equals mu2 does the first-order driving force vanish. This compact equation is extremely general. It applies to exchange between regions, between phases, and later in thermodynamics between reacting species. Whenever matter can move, compare chemical potentials. Matter has a thermodynamic tendency to move from high chemical potential towards lower chemical potential until equilibrium produces equality. A phase diagram is a map showing which phase of a pure substance is thermodynamically stable at each pressure and temperature. The areas are single-phase regions. The curves between them are phase boundaries, where two phases coexist and have equal chemical potential. Consider the liquid-vapor boundary. Every point on that curve gives a temperature and the corresponding vapor pressure at which liquid and vapor are in equilibrium. The solid-vapor boundary similarly gives the sublimation vapor pressure. If the external pressure lies below the equilibrium vapor pressure, the condensed phase tends to vaporize. If it lies above, vapor tends to condense. Thus the curves are not decorative separators. They are experimental equilibrium relations and can be interpreted as plots of vapor pressure or transition temperature under different conditions. This schematic diagram contains the essential geography. At low temperature, the solid is generally stable. At sufficiently high temperature and low pressure, vapor is stable. Between those regions lies the liquid. Each boundary represents equality of chemical potential for its two neighboring phases. The three boundaries meet at the triple point, the unique pressure and temperature where solid, liquid, and vapor coexist. The liquid-vapor curve terminates at the critical point. Beyond that point, liquid and gas are no longer distinguishable phases. Instead, there is one supercritical fluid. Now imagine following a path of constant pressure from low to high temperature. Depending on whether the pressure is above or below the triple point pressure, the substance may melt and then boil, or it may sublime directly from solid to vapor. Reading a phase diagram is therefore reading the sequence of equilibria along a chosen thermodynamic path. Vapor pressure is the pressure exerted by vapor in dynamic equilibrium with its liquid or solid. Dynamic is important. Molecules continuously escape from the condensed phase and continuously return, but at equilibrium the rates are equal. In a closed vessel at fixed temperature, the vapor pressure approaches a definite value that depends on the substance and temperature, not on the amount of liquid, provided some condensed phase remains. Raising the temperature increases the fraction of molecules energetic enough to enter the vapor, so the equilibrium vapor pressure rises. For a solid, the analogous equilibrium underlies sublimation. The vapor pressure curve in a phase diagram is simply the set of pressures for which the chemical potentials of vapor and condensed phase are equal. This links an observable pressure directly to the abstract criterion of chemical potential equality. Boiling occurs when vapor bubbles can form throughout a liquid. The condition is that the liquid's vapor pressure equals the external pressure. If the external pressure is reduced, equality is reached at a lower temperature. This is why water boils below 100 degrees Celsius at high altitude. At an external pressure of 1 atmosphere, the transition temperature is called the normal boiling point. Modern standard state conventions often use 1 bar instead, giving the standard boiling point. 1 bar is about 0.987 atmospheres, so the standard boiling point is slightly lower than the normal boiling point. The distinction is small but conceptually important. A boiling point is never an intrinsic temperature without qualification. It is a transition temperature at a stated pressure. In contrast, evaporation can occur from the surface at temperatures below the boiling point. As a liquid is heated in a sealed container, its equilibrium vapor becomes denser, while thermal expansion makes the remaining liquid slightly less dense. Eventually, the two densities become identical and the interface disappears. The temperature at which this happens is the critical temperature, Tc, and the corresponding pressure is the critical pressure, Pc. Above the critical temperature there is no liquid-vapor phase boundary and no true liquid phase, however much pressure is applied. The material is a supercritical fluid whose density can vary continuously from gas-like to liquid-like values. Supercritical fluids combine useful properties, rapid diffusion and low viscosity reminiscent of gases, together with solvent power associated with dense liquids. Supercritical carbon dioxide is therefore valuable in extraction and processing, including decaffeination, because its solvent strength can be tuned through pressure and it leaves little solvent residue. The melting temperature is the temperature at which solid and liquid coexist in equilibrium at a specified pressure. The same equilibrium temperature is called the freezing temperature when approached from the liquid side. Again, normal means at 1 atmosphere and standard means at 1 bar. The triple point is more restrictive. Solid, liquid, and vapor must all coexist simultaneously. For a one-component system, this occurs at one unique pair of pressure and temperature. Triple points are highly reproducible because they do not depend on an arbitrarily chosen atmospheric pressure. The triple point of water, for example, has played a central role in temperature metrology. Be careful not to confuse a triple point with a normal melting point. At the normal melting point, only solid and liquid need be in equilibrium at 1 atmosphere. At the triple point, all three phases coexist at the substance's own special pressure. The sequence of containers gives a molecular picture of approaching the critical point. Initially, a clear interface separates dense liquid below from dilute vapor above. On heating the sealed sample, more molecules occupy the vapor and the vapor density rises. Simultaneously, the liquid expands and its density falls. Near the critical temperature, large density fluctuations can scatter light, producing critical opalescence. At the critical point, the densities match and the interface vanishes. For water, this occurs at about 374 degrees Celsius and roughly 218 atmospheres, so the vessel must withstand enormous pressure. Once the interface has disappeared, there is no sharp event by which we can label one side liquid and the other gas. This is why the liquid-vapor coexistence curve ends rather than continuing indefinitely. The Gibbs phase rule tells us how many intensive variables may be varied independently while preserving the number of equilibrium phases. Its general form is F equals C minus P plus 2. F is the variance, or number of degrees of freedom, C is the number of chemically independent components, and P is the number of phases. The plus 2 corresponds to temperature and pressure. For the pure substances in this chapter, C equals 1, so the rule becomes F equals 3 minus P. In a one-phase region, F equals 2. Pressure and temperature can be selected independently within the region. On a two-phase boundary, F equals 1. Choosing the temperature fixes the equilibrium pressure, or vice versa. At the triple point, P equals 3 and F equals 0, neither pressure nor temperature can be changed without losing one phase. This is why a triple point is invariant, not a region or a line. Let us apply the phase rule to a one-component, one-phase system, with C equal to 1 and P equal to 1, F equals 2. Such a system is bivariant. We may change both temperature and pressure independently, provided we remain inside the same phase region. If we reach a boundary and two phases coexist, P becomes 2 and the variance falls to 1. Then pressure and temperature are linked by the coexistence curve. Selecting one determines the other. At a triple point, the variance is 0. Notice what the rule does not say. It does not tell us the numerical location or slope of a boundary, and it does not identify which phase is stable. Those require thermodynamic data. The phase rule instead gives the dimensionality of the allowed equilibrium set, an area for 2 degrees of freedom, a curve for 1, and a single point for 0. This labeled diagram unites the phase rule with the geometry of a phase map. Within each colored area, P is 1 and F is 2. Along an ordinary boundary, two phases coexist and F is 1. At the point where three boundaries meet, P is 3 and F is 0. The diagram also illustrates a hypothetical four-phase intersection. For a one-component system, P equal to 4 would give F equal to -1, which is physically impossible. Therefore, four phases of a pure substance cannot all coexist in stable equilibrium when only temperature and pressure are available. The phase rule is doing something profound here. Before measuring any material, it rules out an entire category of phase behavior. Multiple solid polymorphs can certainly exist, but only three phases can meet at any one invariant point in a one-component pressure-temperature diagram. Carbon dioxide provides our first real example. Its triple point is near 216.6 Kelvin and about 5.11 atmospheres, well above atmospheric pressure. Consequently, at 1 atmosphere liquid carbon dioxide is impossible. Heating solid dry ice at ordinary pressure crosses the solid-vapor boundary, so the solid sublimes directly to gas. To obtain liquid carbon dioxide, we must first raise the pressure above the triple point pressure and then choose a temperature below the critical temperature. The critical point lies near 304 Kelvin and 73 atmospheres. Following different paths through this diagram demonstrates that the observed transition depends not merely on final temperature, but on both pressure and temperature. This explains why pressurized carbon dioxide cylinders can contain liquid, while dry ice exposed to the atmosphere never melts into a puddle. Water's phase diagram is unusual in two important ways. First, the solid-liquid boundary for ordinary ice slopes towards lower temperature as pressure increases. Ice has a larger molar volume than liquid water because its hydrogen-bonded crystal structure is relatively open. Pressure therefore favors the denser liquid, so increasing pressure lowers the melting temperature. Most substances have denser solids and a positively sloped fusion line. Second, the diagram contains many solid phases, labeled with Roman numerals. Under high pressure, water molecules can adopt several different crystal packings, each with its own stability region and triple points. The familiar ice in a freezer is ice 1. The liquid-vapor curve ends at water's critical point, while the ordinary solid, liquid, and vapor boundaries meet at a triple point near 0.01 degrees Celsius and about 611 pascals. Helium displays even more exotic behavior because its atoms are light and quantum effects remain important at low temperature. At ordinary pressure, helium does not freeze even as the temperature approaches absolute zero. A pressure above roughly 20 bar is required to produce a solid. The diagram also contains two liquid phases. Helium-1 behaves as a conventional liquid, whereas helium-2 is a superfluid. It flows with extraordinarily low viscosity and exhibits macroscopic quantum phenomena. The Lambda line separates these liquid phases and takes its name from the lambda-shaped heat capacity anomaly at the transition. Different solid structures, including hexagonal close-packed and body-centered cubic forms, occupy high-pressure regions. Helium reminds us that labels such as solid, liquid, and gas are only the beginning. A single chemical substance may possess several distinct phases within the same broad state of matter. We now connect phase diagrams to the thermodynamic dependence of chemical potential. At constant pressure, the temperature derivative of Gibbs energy is minus the entropy. For a pure substance, this becomes partial mu over partial T at constant P equals minus S sub m. Chemical potential therefore decreases as temperature rises, and the magnitude of the slope is set by molar entropy. Gases have much larger molar entropy than liquids, so the gas line falls more steeply with temperature. Liquids usually have greater entropy than solids, so the liquid line is steeper than the solid line. The stable phase at any temperature is whichever line lies lowest. Intersections occur where two chemical potentials are equal and therefore mark transition temperatures. This graphical construction turns differences in entropy into a direct explanation of why heating drives solid to liquid and liquid to vapor. The schematic chemical potential curves make that argument visible. At low temperature, the solid curve is lowest, so solid is stable. At the melting temperature, the solid and liquid curves cross. Their chemical potentials are equal and the two phases coexist. Above that temperature, the liquid curve is lower. At the boiling temperature, liquid and vapor curves cross, and at still higher temperature the vapor has the lowest chemical potential. Real curves are not perfectly straight because entropy itself changes with temperature, but the local slope remains minus the molar entropy. The entropy change of transition can be read from the difference in slopes at an intersection. This picture also clarifies metastability. A phase may persist beyond the crossing if nucleation is slow, but it no longer lies on the lowest chemical potential branch and is not the true equilibrium phase. Finally, consider how pressure changes phase stability. At constant temperature, the pressure derivative of chemical potential equals the molar volume partial mu over partial p at constant T equals V sub m. Increasing pressure therefore raises the chemical potential more rapidly for the phase with the larger molar volume. For most substances, the liquid occupies more volume than the solid, so pressure destabilizes the liquid relative to the solid and raises the melting temperature. Water is the celebrated exception near ordinary conditions. Ice has the larger molar volume, so pressure raises the chemical potential of ice more strongly and favors melting, lowering the melting temperature. Combined with the temperature derivative, this reasoning leads to the Clapeyron equation, which relates the slope of a phase boundary to the entropy and volume changes of transition. The chapter's message is now complete. Phase diagrams are geometric portraits of chemical potential equality, shaped by entropy, volume, temperature, and pressure.